Welcome to week 3. We're really into, yay! This week is awesome because this is the week where we're going to learn the big idea. What we mean by that is this is when we're learning about how soil is built. How soil is built, meaning the new news, what we didn't really know before, humanity wasn't quite aware of in terms of the processes and how nature invented soil building. So that's what we're going to get into today. We have a lot to cover, and we do have a quiz today. So we're going to try to speed through this opening session, okay? So our meditation today, is everybody ready? Let's do a big breath. Everyone online, hello. Big breath, ready? Let's do one more, because I drank a yerba mate and I'm feeling a little bit too excited. Ready? Okay, so today's meditation is coming from Don's brain, and this is what it's about. Don, why don't you lead it? Go ahead.
All right, sure. It's not really from my brain, but it's about flowers. So picture your favorite flower of all times. Go ahead, close your eyes, and think of that. Think of the smell of that flower, the shape of the petals, all the intricacies of all the coloring on it. Especially focus on the color and think about those bright, vivid colors that make up your flower, and where did those colors come from, right? The soil's brown, yet somehow this plant, which is typically green, has this incredible color patterns that somehow materialize out of the earth. So just meditate on that.
That was awesome. Let's get a couple shares. One from in class and one online. We'll start with in class. Anything that you want to share that came to you? Anyone have any ideas? Yeah.
Well, didn't plants start developing flowers because of bees way back like 500 million years ago? This wasps started to realize they need pollen, so the flowers started to grow better petals because they're like arrows to the center, saying this is where the nectar is, and that is why we have all the different pollinators all see differently. So that's why I think the flowers sprouted. That's what I was thinking about, just bees and flowers.
I love it. This wasn't, so everyone's not worried, this wasn't a test. This was just whatever happens, but that'd be a great answer, I think. I don't know. I have no idea. Don, do you have any knowledge if that's, I don't know. I think
I
probably.
read how I'm a beekeeper, so
Oh.
when I was researching it, that's
Great.
Yeah, the change from, because wasps, or bees are just vegan wasps.
Bees are vegan wasps. That's really great too.
I didn't like wasps until I found bees.
Yeah, which came first, the chicken or the egg? I mean, were there flowers and then insects, or insects and then flowers?
I think he's talking about the evolution of the flower petals was the why people wear ties is so that you focus, they're like arrows pointing to the top of their head. You know, those kind of things. I don't know if that's the great analogy. Oh, let's get someone online. What came to you? What moment did you have? Next time you look at a tie, it is an arrow at the person's head. Just saying. Okay, great. Anyone online, whoever shares first.
It's spring right now on the east coast, so there's all of these magnolia trees that are blooming, and so I thought magnolia tree today. I have one right here, and it has these kind of very vibrant, or not too vibrant. It's kind of like a subdued purple at the base of the flower petal. And I'm from Los Angeles, and it's blooming flowers in the spring isn't something that I really thought about until I got here, and I've experienced it for a couple years now. So yeah, that just came to mind. It's the spring bloom that's going on here in Providence, Rhode Island.
It's beautiful. Beautiful that time of year. Awesome. Teachable, everyone's doing amazing. I really love what's going on. We have so many. I don't know if everyone's gone through it. You're not required to, but some of these whys are amazing. really people are putting time and attention towards them. Folks are editing them. Again, these are not necessarily things that you might ever present, but I personally have felt the power that comes when you get closer to what brought you here. So those of you who haven't done it, I encourage you to, and everyone who has, let's give it a hand. These have been amazing to read. We're going to do a quick go around for anyone who had major shifts from last week in terms of the lesson. So personally, when I got into that moment of defining regenerative and got that for myself, it was life-changing. Did anyone have any moments, we'll start with in class, if anyone had anything they wanted to share from either the reading or what was discussed in class, or anything that was like a new view, a new perspective, a shift in your way of thinking? Meadow, yeah.
My husband and I were preparing some of the soil at our house, and I was inside and I hadn't shared with him everything that I was learning in class. And he started breaking up all of our wood sorrel that had started to decompose and was turning brown. And I ran outside and I was like, "What are you doing? You're taking like nutrients from the soil, like what are you doing?" And I got really upset and he was like, "No, we can't put our mulch down, it's gonna be too high." And I kept saying, "But we have to leave this, and there needs to be compost, and then there needs to be the wood." And I was like trying, and I couldn't get it all out because I was so emotional and like trying to tell him like, what, you know? And so we had like a moment, and I kept saying, "I can't explain it to you in this moment, but I need you to just trust me for a second because of everything I'm learning, and then I can put it into words in a few moments when I have a second." The end of the story is that he took it all out of the trash can and dumped it back onto the ground for me, and then I got to have a conversation with him about why.
Yay! Activation. Yeah.
So I have one of my projects. My project is a school garden. So it's kind of a macro of the greater farm micro, or vice versa. You know, I'm nervous. I'm going to force myself to speak every class. So at the end, you'll be like, "Jerry, will you just stop talking?"
Go for it. That's what we're here for.
Nervous. So the last year, I have a parent that is just like anal, like rows and completely tills everything, and we've had to pull up the sod, and it's just been insane. And I've tried to communicate it to him in a way that is about nature and permaculture, but I didn't have the language and I didn't have the passion until I started, immersing myself in this conversation. And as I'm immersing myself, and I think because you're always presented in a positive, non-judgmental, way, I was able to do that with him. And now, the last time I said, I think we should do cover crops before the summer. And I know that's different than because we're just in the spring. He's like, "No, we got to do this, and I want to do this," and whatever he was saying. And then I got a text that night, and he sent me a film on the living soil. And he's like, "Now I finally see what you're saying." And I was like, "Oh my God!" I started crying. I was just like, "This is so amazing." And now our garden is, he's like, "We spent all this time," and I was like, "Whatever." So now my new story for the garden, because I have a nonprofit I started, and I didn't know what the conversation was going to be. I didn't know the about us until now, and I do. And it's the school gardens can be that the little micro for these carbon farming.
Yeah.
I'm so excited. I just have to, yeah.
That's wonderful.
A bell just rang. I loved whatever just happened. It's like, ding, yay. Yes, awesome. Online, anybody have any moments that they want to share from last week, thinking regeneratively, acting regeneratively?
Yeah, I did read The Conquest of the Earth, 7,000 Years, and I hadn't read it before, and it is just mind-boggling. It is just the history of degenerative agriculture over the whole planet and what happens when you just don't pay attention to the land. And it's such a lesson for people. And the amazing thing is that he wrote it in 1939. He was not talking about today. And really, regenerative agriculture improved after the Dust Bowl and people became conscious. But now we're kind of going the other way. So it's up to us to take his lessons to heart and make people aware of what he learned. So that was great.
Awesome. Thanks for sharing that. Yeah, the Yellow River part of that story was the most shocking. Awesome. Don, Sunday session with Isabel. Can you share how that went and a little update? So Isabel is a friend of ours, a post-soil advocate graduate, and she, with a couple other folks that we know, passed the Healthy Soil Act of New Mexico. And Don hosted her. How'd that go, Don?
It was fabulous. It's all recorded, so I would encourage people to watch it. She comes in about half an hour into the Q&A session on Sunday night, so you can skip some of the other stuff if it's not interesting and go straight to her. So here's a former graduate with no degrees in law or policy making or anything, just someone that has a passion. And she used a whole bunch of our material, images, etc., to help promote this. And she got a kind of a crash course on how can I share this information with really conservative people that want nothing to do with, anything to do with climate change or whatever language it was. So she had to speak everything from conservative to liberal and change phrases. They had, not just climate change was, oh, you can't say that in the bill, but even the word carbon was divisive. So they settled on soil organic matter. Everyone was like, oh yeah, soil organic matter is fine. We can talk about that. Just don't mention carbon or climate change. And so it was really fascinating, all the stuff that she learned, and also to see our very own material, which she also shared with us. And you're welcome to look at all that material. But she took images from Kiss the Ground and used them liberally in their brochures and pamphlets and educating legislators. And they passed this act. It was fascinating to see a state adopt a policy with the 5 regenerative principles in it. And that was basically what she learned from our class. So really inspiring I was just blown away that one of our students did something like that. It was great. So highly encourage you to watch the Q&A.
Yay, Isabel. This Thursday, superstar. This Thursday, Kiss the Ground has a really fortunate opportunity. We are the grantee, or whatever you want to call it, of Whole Foods. They do it twice a year, 5% day, goes to a nonprofit every year. We are the chosen nonprofit for this half of the year. So Thursday, if you're interested, anyone in LA or anyone online who's in the Southern California region, you can email Karen@kisstheground.com to find out where we are. We're going to be at 4 different locations, one down south a bit, one in Venice, and a few others. I don't know exactly where they are. But if you want to come table with us, we're going to be tabling from 11 o'clock to 1 o'clock at the Whole Foods, talking to 2 o'clock. Sorry, 11 o'clock to 2 o'clock. So if you want to do that, it's an opportunity. If you're new to advocacy and just talking, I'll be at the Venice one, and several other Kiss the Ground members and some ex-advocates will be there. So it's a good time to practice your talking points, practice just pitching to people. It's kind of like that knocking on doors kind of style where you have to try to get someone interested. It's gruesome sometimes, but it helps get your practice in. So if you're interested, email Karen@kisstheground.com, and she'll let you know which locations are closest to you, or you can let her know, or just say, hey, what are the 4 locations, and you can pick one, okay? All right. Our first quote of today, we have one. It's from, how many people picked Call of the Reed Warbler for their book? And then we're very surprised at how big it was. Nobody? One person, awesome. It's to me, it's the best yet on regenerative agriculture books, but that's my biased opinion. But the quote today is, the solar energy function, and it is talking about focused on maximizing the capture of solar energy by fixing as many plants' sugars via photosynthesis as possible. That's the big, it's not worded very friendly to most folks, but that's what we're going to be getting into today, is really understanding from a basic point, more basic than this, how the system works and how how amazingly engineered and crafted nature has developed this amazing capturing system of energy and carbon, of course. Yes? Flashcard updates. Kevin went out of town, and then he posted.
Twice, and I just posted them in third week too.
Great. So now they're on second week and third week on the comment section. So they're on this week. So people can just look at this week. So that's the online version of the flashcards. Let's check that out. All right. So we're going to do our first exercise today. We're going to break off. What the exercise is you get into a partner. So this exercise is pretty simple. You break into partners, and the first person asks, why does soil erosion happen? They ask that to you, and you respond to them. You explain why soil erosion happens, and then you switch, and the other person, and if there's any corrections or if you have some note for your partner, we say, oh no, what about this thing, and add something really quick, and then switch, and the second person asks, how do plants and organisms build soil? And this is kind of a pre-thing for your quiz that's coming, so it might help. So we're going to do this exercise really quick. Michelle, are you ready to partner people up? All right, so partner up here. We're going to do pretty much 2 minutes. We should be able to do this. Just quick, ask the question, person answers it, switch, and we should be done in 2 minutes. So people online, you're going to be called back in about a minute, but know that it'll take a full minute to get you back so you can keep going. All right, ready to go?
Can you repeat the question one more time for the online people?
Yeah, they're on your Teachable. Get a partner. The first question is, why does soil erosion happen? The second question is, how do plants and organisms build soil? Let's get really quick, just one from in class, because we're going to move on to the next section. One thing that you heard from your partner that was like, wow, that's a cool new nugget that I'm going to steal of how to explain this or that. Anybody have something that they loved how their partner shared it, or a new perspective their partner shared? Yeah.
So Jason very aptly summarized that he said when soil is able to breathe, that means it is building and that it's alive. I thought
Nice.
that was so beautiful.
I think that's really beautiful. Great.
I don't know where I stole it from, but
No, sometimes this stuff just downloads. You never know. Awesome. All right, we're gonna do a 15. I hope we switched the order because I wanted y'all to get your brains going, because sometimes jumping into a quiz is weird. So now we're gonna do the quiz for 15 minutes. Folks online, the link is right in Teachable. Everyone here, the link is right in Teachable. Please do not Google the answers. These are not really graded other than to give you feedback on how to get better at this. So there's no point in cheating because you're just trying to figure out where you're at right now. Okay? Ready? And does everyone have the link?
No.
The link is on Teachable. Right? It's right above the quick exercise. Underneath flashcards, it says first quiz, 15 minutes. The link is right there. Yeah? First quiz.
Are we allowed to look at our notes?
No. No looking at notes, no Googling. And we're going to go. We'll be back in 15 minutes. It's 7:23 now.
Wait, okay, got it.
Go ahead.
All right, good luck, everyone.
All right. So we have Don Smith going to take it away for week 3. We're starting with, what is soil? Don, you just tell me when you're ready for next slide, and I'll just.
Next slide, just kidding. So this is normally where it's very awkward because I'm not in class and I'm going to ask the people that are in class, not online. So what is soil? And since I can't see who's raising their hand, just somebody blurt out what they think soil is and don't look ahead.
It's a living organism.
Excellent. What are the components that make up soil?
Humus.
Bacteria, fungi, soil aggregates.
Don, are you hearing these things?
Yep, yep.
Keep them firing,
Keep
folks.
coming. Don't be shy. It's a public speaking class.
Water, air,
Water and air. We had water and air, Don.
carbon.
Somebody looked ahead.
Sun,
Someone said carbon. Someone said sun.
air.
Oh, I like sun. That's an interesting one. I'll have to unpack that one.
Which one?
Sun.
We have Don. So far we have air, water, humus. Some of the biology was mentioned. Someone said carbon.
Yeah.
Silt, clay, sand.
Oh, we got someone just said sand, silt, and clay.
Oh, minerals.
I love it. All right, so I think we got it covered for the most part. So we'll go to the next slide now. So whoever said air, let's talk a little bit about the air. Who can tell me in the class what the air is made up of? What chemical elements are in air that we breathe every day?
Nitrogen.
All right, whoever said that gets an A. How much percentage of the air is nitrogen?
78.
Another A student. We got 2 A students.
All right, what's the next ingredient?
Next biggest ingredient.
Oxygen.
Yep, percentage?
21.
All right, so 21 and 78 is 99. How about the next one?
Argon.
Oh, somebody's really been reading ahead. Okay,
Yeah.
so
Water
argon's
vapor.
about,
Water vapor, that could be 1 to 4%, so.
well, yeah, but that's actually a combination of things. But anyway, basically, we've covered almost 100% with 3 gases, nitrogen being the main one. What's the largest fertilizer that we use on the planet?
Everyone said nitrogen. Everyone said nitrogen.
Okay, and if nitrogen is 78% of the air before, and all plant life worked just fine before we started making nitrogen fertilizers, why do we make nitrogen fertilizers?
Ignorance.
Who said someone said over here?
Because they sell well.
Oh, because they sell well. Oh, they said something else. That's true. They do.
Nutrient availability.
Yeah, that's part of it, but part of it's because all the things that take nitrogen from the air and fix it into the soil to make it plant available, we've managed to disturb that process greatly. So nitrogen fertilizers do really well in a damaged ecosystem, but if you put them in a highly functional ecosystem, you really don't get that much bang for the buck. But anyway, so air is a big component, and oxygen's really important component of that, as well as nitrogen. I can't speak to argon. It's an inert gas, but really nitrogen's the big one, oxygen is second. Most people, when you ask your audience, unless they're smart like you guys, have no idea, and the most common response is what's the main ingredient in air you breathe is oxygen. And most people don't understand that nitrogen in the air, they actually take that nitrogen from the air and make fertilizer out of air, right? That's how nitrogen fertilizer is produced, is used a lot of energy, but they're actually taking that nitrogen from the air. So little tidbits, trivia. Water, another huge component in the soil. So if you have too much water in the soil, where does your air go? Out, right? So when a soil is flooded, that's a bad thing, but you definitely need to have a good, healthy amount of water in your soil to keep the plants going. And then let's talk about these other pieces. We'll go into sand, silt, and clay in a little more detail, but those are the actual mineral components. Where do sand, silt, and clay come from?
Minerals.
We got rocks here.
They come from minerals, the bacteria, could be, et cetera, et cetera.
Well, they
And also
actually,
mycelium.
they do contain minerals, but the sand, silt, and clay themselves come from the parent material, which is generally some type of rock that's been broken down either by some type of microorganism like lichen, or also just soil biology and lots of weathering as well. So sand, silt, and clay are really just very small rocks, if you want to think of it that way. And then we have the last component, which we talk of as organic matter, which is really an amazing piece of the puzzle. It's not a huge one, but it's super powerful. And you all know that part of organic matter is what chemical element that's really important?
Carbon.
Yes. Who said that?
I did, Elliot.
Elliot, another A. All right, he's on a roll. So let's talk about what is organic matter. Anyone want to take a stab at that without reading from their notes?
Things that are alive.
That's part of it.
Things that were alive and are now decomposed.
That's another part of it. So basically, the organic matter is everything that is alive or was once alive. That's pretty much everything living or dead that was a carbon-based object. So these are just
and the byproducts of living things.
Yes.
Yes.
So you can have a leaf that fell off a tree and then gets decomposed in the soil by all sorts of biology, and all of those pieces, the biology that's dissolving it, the leaf itself, those are all organic materials. It could be a root, it could be a living root, it could be a dead root, and it could be a microbe, partially digested microbe, totally decomposed as far as it can go, in which case it becomes humus, and that's all part of organic matter. So let's go to the next slide, then. And we'll talk about sand, silt, and clay. Not very exciting, but for those of you, when you're presenting it to your audience, you can just talk about these different size particles. People grade soil by the percentages of sand, silt, and clay, and if you get a rich loam, it's a certain percentage of sand, a certain percentage of silt. It's usually like perfect is 40-40 and 20% clay. You don't need to know that unless you're talking to a gardening group, but the main thing is, who here thinks you can see a clay particle? Like, you've all experienced clay, but can you actually see clay with your naked eye?
Not the individual particle.
Right. The individual particles are so small that you can't actually see them. They're like 20 microns or smaller. So super duper tiny particles. But yet you know when you have a clay soil, it's really hard, it can be really challenging to work with, or it sticks to your shoes when you're walking around. So everyone can relate to stories like that. But really, you just need to know it's a really fine particle. It's very good at holding on to elements. It has, it's a charged particle, and it's really good at holding on to minerals. So people complain about clay soils, but they're also great soils to have because of how they hold on to both water and minerals. Whereas if you have sand, most of your nutrients will not stick to the sand particles, and nor will the water. So it just flows right through, and it's hard to build organic matter in a super sandy soil. It's totally doable. It's just challenging for most people because everything just runs right through. But as you build organic matter content in, whether it's your sandy soil or your perfect loam or your clay, it does amazing work, and it can hold on to all the nutrients and the water. And that's really what the goal is. So
And it starts to break down the sand to finer particles as well. Yeah.
Right. So everything is constantly being eroded, if you will, by biological activity as well as physical and chemical properties. But a lot of it is the biology itself breaking down these particles, extracting nutrients. So when people say, oh, my soil doesn't have any nutrients, actually it has plenty. It's in the sand, silt, and clay particles, but it can't access them because the biological system isn't working as it should. So let's go to the next slide. Okay, so once again, this, I want you to know, this is a sample picture. Do not think all soil equals these percentage numbers. We should almost take the percentage numbers off. I don't want you to think that, oh, all soil has 5% organic matter and it's all broken out this way. This is just a sample. And as presenters, always beware of any slide you use where you put a fixed number on it, because people fixate on those numbers. Does anyone want to say what they thought they heard me just say?
That your audience will fixate on a number
Yeah.
if it's, if you don't give it context.
Yeah.
Correct. And so just beware, anytime I show slides that have numbers, I always find that people tend to fixate on the number, and then they're like, well, I have a different da-da-da-da-da, or this report over here said that, how do you reconcile? So it's just something to be aware of as public speakers. If you're using a slide with numbers, really make sure that you make a point that either this is just an example, and even when we say that, people still go back and say, well, you said it was 5%. And it's like, no, I said that was an example. So just beware of that. And going back to that slide, if you want to look at the organic matter component, and I don't have that up on my screen, full screen, 1 second. I have to blow it up here. Because I can't read the numbers, but
This is generally, Don, I'll just tell you, this is what most textbooks will show you for a generally medium grade healthy soil. This is what their example is. So this is, again, these numbers aren't valid because they can completely vary depending even on seasons. So what we're trying to say is that this is a generality of what you'll see in textbooks often.
right. And you'll see, so there's a big section there that says humus. And if you start going into that, people will say, well, what is humus? And there's descriptions of it, but so far, nobody's really been able to define it because it's so many, it's a super complex molecule, and it's basically organic matter that can't be decomposed anymore. But there is no such thing as the perfect humic molecule. It's got zillions of forms because it just takes on it. It'll have different atoms of different minerals attaching to it constantly, and it's actually evolving and changing as it's hanging out in the soil. So we just kind of lump it together and just say humus, and that's a big part of that organic matter. And then you've got smaller parts that are decomposing. Some is dead, and it's just kind of this mix of different materials, living, dead, and you shouldn't be able, once it's fully decomposed, you can't tell what it is, right? If you pick up a handful of soil, you might see a twig in there or a root, but once it's fully decomposed, you can no longer tell that it was a twig or it was a root or it was a mushroom or whatever. It's completely decomposed. Who here smelled forest floor after a rain, or rich earthy soil, or compost, right? Those smells, like, you love that. I don't know, maybe it's just me. I love that smell of rich soil or fresh, fully decomposed compost. It's amazing. After a rain, if you're walking in the woods, that smell, it makes you feel good. And they actually have science that it does make you feel good. The Japanese call it forest bathing. There's a bunch of healing properties just being exposed to that type of air. Anyway, that's a side note. We'll go to the next slide. I covered everything on that one.
So what happens if SOM changes?
Yep. I'm following you, Spin. So this is a question for the audience. Can you guess, does someone in class want to take a stab at that? What happens when soil organic matter changes? Erosion. Okay.
Change the weightability?
Yeah. And so if we think of it as, let's go from a low soil organic matter to a higher soil organic matter.
Think in positive, people. Yeah.
Increase water retention capacity.
Nice.
That's excellent.
More light?
Carbon to nitrogen ratio increases.
Let me think about that.
Yeah.
You could say that.
Increased nutrient availability.
Increased nutrient availability, totally.
Yep.
It feels spongier.
Maybe it is spongier. Yeah.
Yeah.
Definitely feels spongier.
Anyone want to talk about what's one of the big components of soil, and does that improve?
Fungi.
We talked about water, but we forgot one of the other ones.
Increased carbon storage?
Yes. What's one more that we forgot? Someone mentioned
Air.
air.
Right. So think about that difference when you go and you take a soil that doesn't have a lot of organic matter. Generally speaking, it looks more like on the left, right? It's more compacted and there's less airspace than a healthy soil with more soil organic matter. So it can infiltrate water better and air. And gas exchange is super important because plants, one of the limiting growth factors for a plant is how much CO2 it can get. And good air exchange means CO2 is leaving your soil in the form of oxidized organic matter and going up into the bottom of a leaf, which is a wonderful thing. So, good things. Do you want to go to the next slide, Ben?
Yeah.
Okay, so this slide is, once again, it has numbers. Does anyone remember what I said about numbers? People are going to say, well, this bad soil over here switched to this one, and these were the percentages. These are all samples. So don't get hung up on the numbers and think, oh, my good soil has to be 40% air and 30% water.
And just another thing to remember, like this soil here could be like this. If it's good conditioned soil, we have a nice rain and it's totally moist. You could still have really great aggregated, amazing soil, and 3 months later, no rains, it's dry, but it's still able to jump up to 30, maybe 40, 50%. So again, these numbers vary, but the point is they can change from this. This one would have a harder time becoming more water. Does that make sense? Great.
Right. It couldn't absorb, it doesn't have the organic matter and the structure, which is, we're going to talk a little bit more about structure later on, but basically when you look at how soil is formed and aggregation of soil, which is just how the little particles of sand, silt, and clay and organic matter get stuck together, when you have more organic matter, you have better, what the term is called, aggregation. So soil aggregates form around organic matter. And it's amazing when you see a healthy soil, how it feels light and fluffy and it can absorb water, it's got good air exchange, good nutrient exchange. It's a huge difference of what that soil looks like, whether you put it under a microscope or you just hold it in your hand. Or if you lift up a weed or any plant from a really healthy soil, there will be a whole bunch of particles, soil aggregates stuck to the roots.
And we'll have that next week for everyone to touch and feel. Yeah.
Yep, you'll get to see that next week. So we'll go one more slide to close out with Ray Archuleta, right?
One second. I just want to say, so on my original slides, I just added the word compaction and aggregation. So for your personal slides, that's what Don was just talking about. When we look at this chocolate cake structure over here, we're really looking at that aggregation. And that aggregation, and we're going to talk about it more in a minute, is what allows for the airspace and the water space to happen, as well as the absorptive capacity. But just look at how dense this, you can feel the density of this soil on the left here, right? It's visceral, you can get it. Cool?
So with healthy aggregation, those numbers can be different. You can just have healthy aggregation?
Yeah, I mean, the numbers can vary. I mean, the soil organic matter number would be a soil organic matter number, and that could vary also. But each of these is variable completely, but the point is that the capacity of this one on the right is far superior than this capacity on the left.
Yeah, and let me add to that. So I'm getting very familiar with organic matter content in a lot of the soils in California, as well as other growing areas across the West. And we're seeing in conventional ag, in most ag, organic matter, soil organic matter at about 1%. And this goes throughout the Central Valley of California. We used to have way in excess of 10% soil organic matter throughout the Central Valley. And we're down to less than 1%. And it's really hard to go less than 1% because there's some that's just kind of permanent. And that's where we're at. We've destroyed the organic matter content in our soils, which means we've lost nutrient cycling, water absorption, air exchange, all of that. And now we suffer from massive erosion problems. So soil organic matter is amazing, and we're going to talk about how we can build it back because we need to start practicing regenerative ag.
Thank you. Awesome, Don. I just wanted to have people visualize this for a second. When we're talking about this sponge, right, this chocolate cake sponge that we're looking at here, and this green grass. So imagine you personally go out and you fill 5 gallons, and it all absorbs in a couple seconds because this is really spongy, right? And then you have plant life on top. And plants are cool because we're going to talk about this more later, but they actually take in heat and use it for energy, so they're actually endothermic, meaning they're putting out cooling effect. So these plants are not only shading the ground, but they're actually creating a cooling air conditioning situation. So this sponge, like a wet sponge that you put away in the shade or in a cool area versus a wet sponge that you put outside in the sun. So when we think about how much water could infiltrate and be held in this soil, let's say it rains and an inch of rain absorbs in 4 seconds. Over here and around the United States, as Don mentioned, with these degraded soils we're dealing with, infiltration rates at 1/2 inch of rain in an hour. So that means that the water is just sitting on the top, and that tendency then with degraded soil will be that it is eroding off and or evaporating. Losing, if it's pooling, we're losing 70% to 80% of that moisture content within a day to evaporation. Over here, we're saving it. So just when we conceive what farmers are having to deal with, when their situation is like this, they're having to water more, they're having to add more fertilizer, everything becomes more and more work. And that's the trap that so many farmers are in. And we're saying if we build this scenario back, it's totally possible. We can build that on top here, and that's what we're going to talk about. All right, let's take a quick stretch break. Stand up. Everyone online, stand up. And Michelle, can we pull up everyone online? Thank you, Don. Let's give it up for Don.
I want to add one thing while you guys are stretching. I just want you to note that Finn said an inch of rain absorbs in 4 seconds, and 1/2 inch of rain absorbs in an hour. That's a pretty big difference. That's it.
When we talk about flooding and mudslides and all these things that we're dealing with all the time, oh no, there's a drought. Anyway, I'm giving away the rest of the class. No one's going to come next week. All right, let's sit back down. Everyone get a good stretch. Let's take one more big breath. One more time. So one of the most exciting things about this topic is how new it is to almost the entire population. And you're going to hear me saying this over and over again. I said it earlier. I'll say it again. But the fact that most of our soil scientists, most of our people who are working for the NRCS, the Natural Resource Conservation Service, which used to be the Soil Conservation Service, most of the people who are, arguably, most of the people in universities who are teaching soil science, a lot of this information that we're now giving out and now is accessible to more and more people is very, very new. Okay? We're going to be getting in it, but just for one example, everyone remember what mycorrhizal fungi is? Have you learned it somewhere? The discovery of glomalin, which is the most biggest part of aggregating soil together, the glomalin that is on mycorrhizal fungi, which we'll talk about in a second, That was discovered in 1996. Most of us were born before 1996 in this room. So just recognizing how recent that is in science is really important. So when we start to talk about someone like Ray Archuleta, who had 25 years experience in the NRCS as a field agent, him saying we didn't know how the soil really worked, grasping that for humanity, this is an amazing opportunity. So when you're presenting this out there, reminding people, I'm not just here giving you another thing that has existed for 55 to 1,000 years. This is a big epiphany for the people who supposedly knew and were teaching it. Does that make sense? So we're on the frontier of soil science with a growing movement. Like, that's how big this is. This is something that is revolutionizing how people are thinking about farming, how people are thinking about soil science. So this is up here, and I encourage you to use something like this to remind people that most people didn't know, most people don't know. This is vacant from most textbooks on how soil really works. Okay? So we're getting a question, yeah.
Did we know this and then we just chose to forget it, and then now we're relearning it, or it's just
So
we never
great question. So when we look at some ancient cultures of figuring out how few and far between, we're actually figuring out how to have continuously regenerative production of food for their communities. The discoveries that we're talking about today weren't there. They couldn't stand up in front of a room and be like, we know with this certainty now how this actually works. The fact that it worked, that's a different type of knowledge. Like, oh, when we do this, when we let the plants here, it makes the soil better. If we always take the plants off and let it bare, it'll get compacted. You can know that, but knowing how and why is this new thing. So when we're talking about, we now have the backing of the science understanding of this, which makes it so when we're approaching policy people, when we're approaching businesses for investment, when we're approaching folks who are going to say, tell me what you actually mean, we have that now. So that's what he's saying. We didn't really understand how the soil worked. You can go back in ancient cultures that were doing it right, but again, they didn't necessarily have the science of how it worked. They didn't have the microscopes to think about discovering glomalin. Like, that was not really possible to fully grasp. So this is a really helpful slide. Current conversation, carbon emissions, reductions, all this stuff is carbon talk. And generally, when you're talking with your audience, most people have this negative connotation with carbon. We have an opportunity to eradicate that, okay? So we can just come out and say carbon is not the enemy. You can change the slide. You can say carbon is not a problem. You can even say CO2 is not a problem. You can go that far just to mess with people's heads, to be like, oh yeah, let's get this straight. Why? Because everything alive is made of carbon. How many people got on the test, where does the structure of a tree come from? Everyone get that right? Mm-hmm. From the carbon in the air. We're going to get that in a second. So any questions on this? Anyone want to say this out loud? What you heard me say was?
Carbon is not the enemy.
Right, carbon is not the enemy. Cool. So another thing.
That's super important.
Yes.
Why is it super important?
Because I'm from Alberta and everybody pays a carbon tax and they are righteously mad because of it. And that's the wrong statement.
Right. So thinking in the context we're living in right now is silly. That carbon is the enemy. Carbon's just out of place at the moment. And we have an opportunity to put it back where it makes the most sense in the soil.
This is like your global warming compared to climate change type thing? Like, you gotta change the dialogue?
Yeah, I mean, if you're thinking,
I guess?
if you're thinking that way, and if you're thinking of trying to bring people who, we were talking earlier about Isabel's situation, you can't say carbon. If they came out and said, we're all in agreement that carbon's not the enemy, we're not saying that you have to, be against carbon. This is a positive thing. Encouraging you to use it to change the conversation. Yeah. So this is another thing that I personally think is really important. So I have several friends who are very smart and in their own fields, awesome people. But when I start talking about timelines, I feel like people are mixed up. And I personally can't fathom it either, but I try my darndest to. So why I have this slide is for you to use for your presentations or people or for yourself to really work. Say, hey, everyone in the audience, let's really try to imagine how long ago 500 million years is. So what I'm saying is, when I was referencing my friends, I will say 300 million years, I'll say 20 million years, I'll say 15,000 years. Some people I talk to, it's just like, yeah, a long time ago, all lumped together. And I'm like, that's not actually okay for me, because it's disrespecting the research and development that I'm presenting to you. Does that make sense? So if someone had an advertisement, we've been working on this product for 100 years, you'd be like, wow, this company's really been researching and developing. All the drugs we get now are like 5 years research and development. You're like, wow. When we talk about 500 million years, if you're just lumping that up with 20,000 and 50 million, that's not okay for grasping how amazing what we're about to talk about is. Does that make sense? So this can be used to set the stage for people to be like, look, this is a lot of time that nature has been perfecting what we're talking about. Okay?
How old is the Earth?
4.7 billion or 4.6?
8, I think.
4.7 or 4.6? One of those two. I forget.
That's not good enough for me.
Google it. We're actually, I think we should do a quiz next where it gives people practice on just Googling stuff, because too often people ask me a question and I'm like,
Google it.
Your phone. Okay.
I mean, that's the correct answer too, right?
So what we're saying, this slide's also important. The next big reason it's important is, what are you seeing here?
Nothing.
Rocks and desert.
Rocks and desert. What did the Earth used to look like over 500 million years ago? Rocks and desert. Why?
No life.
Huh?
No life
No life on land.
on land.
Where was all the life? In the ocean. So billions of years, couple billion years of life in the ocean, while the land remained desertified and hot. We had some fungi and some bacteria, and then lichens started to evolve. But generally, what we're talking about is a vacant landmass. And talk about high CO2 levels. Jesus. I'm sorry, I shouldn't say that, but it was a lot of CO2 in the atmosphere. It was very hot. It was not a good place to live. Then we got the balanced climate, fresh water, and fertile soil. The ability for life as we know it to actually work on land. So that is because organisms came out of the ocean and were able to do what? We got another A student in the crowd. Photosynthesize, yes. So that is that process. So it was happening in the ocean for a while, and then it came out of the ocean and actually started to work with the bacteria and the fungi to harvest minerals, and that's what we're going to talk about today. So this is a useful way. So a lot of the presentation materials I'm giving you are tried and true brain explosion moments that a lot of people have. So you had in your quiz today, where does a tree come from, or where does the structure of a tree come from? So when you're presenting, I've had some of the smartest people I know still text me and be like, yo, that where did this tree come from thing, still blowing my mind. This is useful. I'm telling you, tried and true, really intelligent people don't really know. So you ask an audience, what's the answer? Where does the tree come from?
Air.
Air. What in the air?
Carbon.
The carbon in the air. The structure of the tree comes from the carbon in the air, or any plant, right? So when we think about that, what we're trying to relate, and you can tell your friend, you can be in line and be like, so you see that tree over there, where does it come from? People are going to be like, most people are going to say the soil. 90% of the time or more, they'll say the soil, the seed. People will be puzzled. They'll be like, yeah, the roots are in the ground. It comes from that. That's what most people's mindset is. That's what my mindset was. It's generally how people are thinking about it. So then you can add. So if it came from the ground, there'd be big holes in the ground, right? There'd be these giant vacant spots because it took all this stuff from the ground, right? Yeah.
That what was in video, the soil video that we watched.
The soil story?
The soil story in the tree. They explained it, well, each one explained the same thing over and over, but I think it was by the second one I got it, like, life just comes out of air.
Yeah.
That is pretty much.
So that's exactly where I was leading to. So what Meadow's saying is that life comes out of air. So what I think is so fascinating when you're explaining this to someone, having this little fun, again, view change of someone, be like, the stuff we call nothing, how often do we refer to this as nothing? Very often. Like, this is our concept of nothingness. Is the source of everything, because we are structurally carbon, though we're mostly water, and most plants are actually mostly water. The structure is carbon. So we are all carbon structured creatures, all of life. But it comes from thin air. Does that make sense? The carbon that made this tree did not come from the ground. Everyone say that?
Yeah.
People still get it confused. Be like, yeah, I know that most of it comes from the air, but yeah, most of it, a bunch probably comes from the ground. No, no. The carbon came out of the air. We'll talk about which parts of the air, but it came out of the air. All right, anybody want to take this up? Here, let's do it. Someone do the tree example. Who wants to volunteer? Come on up. Anybody?
Public speaking class.
Public speaking class. You want to take a shot? You're just running through this little thing as a presentation, pretending you're doing what I just did in a shorter fashion. You want to take a stab? All right.
Take a stab.
All right.
All right. Can I use the clicker?
Yeah, but you won't switch. You're just going to stay on this one.
Oh.
Yeah.
Oh,
Which one did you want to go
that's
to?
fun.
I know, but we're just doing a short one.
Well,
Oh.
so, if I had to ask you all one question, let's get a little thought-provocative here. Provocative. Where does a tree come from? Any ideas?
The ground.
The ground.
A seed.
A seed. So walk me through that process. What would it mean for a tree to come from the ground? Like, what would that process look like?
The roots go into the soil and grab little pieces out of it and move it up the thing and turn it into a tree.
Yeah, they like digest the rock and make it into tree.
Wouldn't that involve like a lot of space taking? You know, like kind of cart these like sinks in the ground that just kind of appear out of nowhere. Like, where do all of those little particles? Where do the roots? Where do the rocks? Like, where do they get all of those foundational ingredients to then build the tree?
I think you just rearrange it, like, you know how you can make it look like you have more stuff. So I think maybe that's.
So I'm gonna blow your mind. Get you thinking at a super granular level. I'm gonna say that trees come from air. From the very, I know, mind blowing. Like, blows your mind like a root aggregate blows up with nitrogen and phosphorus and all of the things. And I'm gonna stop there because
Yeah. Great energy. Awesome. That was great. So then you can go and you're talking about, so plants and trees built from thin air, okay? So we're indicating that CO2 with an improper 2 number, pardon that, that's a long time ago. Isn't that supposed to be on the bottom?
Yeah, I mean.
Someone else made that a long time ago, and I can't adjust this slide because it's embedded in it. This is not movable, so I have to put something over it. Trees and plants built from thin air. So you're basically saying that this is where they come from. And we use this as photo-freaking synthesis. So that's what we're talking about. That's the big idea that we're saying that's so cool. So what's happening is plants are pulling in CO2 into their leaves and using the energy of the sun to combine them with hydrogen and oxygen that they get from water, H2O, that they pulled up, and they bind those. They make an energy bond. That makes liquid sugar, the sap of a tree. Is everyone, when they were kids, you can use this to remind people, be like, the sap, the liquid that's in a plant or a tree, that is the liquid carbohydrates that the plant makes to build itself. Yes?
Mm-hmm. One more time.
You do it. You do it. Just try it. Just try it. So,
please. One more time.
Someone else want to do it. Let's have someone else do it. Someone online want to explain this one? Explaining the photosynthesis. Yeah, go ahead.
So the plant takes the heat from the sun, and then it mixes with the water that's pulled up into the
Uses the heat, the
Uses
sun
the heat.
energy.
the sun energy to mix with the water and other nutrients that are fed up through the leaves and create these liquid sugars.
It's pulling what into its leaves? Carbon dioxide.
The CO2 and the water, like exactly the carb. That's where it's created. No,
Right. So it pulls the CO2 into itself, right?
and the water creating the liquid sugar.
And uses the energy of the sun to combine carbon and hydrogen and oxygen to
Okay.
make carbohydrates.
Okay.
The liquid
So
sap.
it's the heat combining. No, it's the heat is needed to combine the CO2 and the water.
Yes.
Okay.
Sun energy.
Oh,
Yeah.
yeah, I was gonna ask you to clarify, because I was thinking it was the light, and I was thinking like
Yeah.
some magical light waves.
It's not to say heat. Heat is usually what breaks them apart and burns them. That's the process of how we make energy, how we metabolize things in our body. So the sun energy is a better way to say it.
But does the heat and the light, or some energy?
It's utilizing the energy. It's like if you plugged a tree into a socket, the energy it's using to combine those. It's like a solar panel. So it's actually making energy.
Is a better word than
Yes,
heat.
yes, for that energy. Question, yeah.
Yeah, so if we're saying that the tree is made from air, but do we need the leaves first? Like, because you're saying, all right, you need the plants first, because the plants are pulling in the carbon, so isn't the seed, like, is the seed sprouting first, and then that's what's built, and then photosynthesis happens, and then that's what's building the tree?
So
Can I answer that?
Yeah, go ahead, Don.
So yes, when a seed is first germinated and there is no leaf, that's using the energy that's in the actual seed itself. But you'll notice that it's a cotyledon, the first two leaves that pop out of that shoot, they immediately turn green and start photosynthesizing. And from that point going forward, they've pretty much used up the store of energy that was in the seed, and now it's all being driven by photosynthesis.
Right. So it's just the initial seed pop. Does that make sense?
Is it fair to say that the more lush the tree, the more photosynthesizing that's happening also? Just because of pure...
Yeah, maximizing photosynthetic capacity. I mean, not all leaves are getting
They're not all
equal photosynthetic capacity because they're in shade and they're not operating at the times all the same. It does change. And that's why the sun is moving and yeah, so it depends. And sometimes, we'll get into this later of how their trees are sharing with each other if they need to, sharing sugars. Any other questions? Yeah.
So then would the answer of where does a tree come from more be like from photosynthesis than from just like the thin air? Because it's coming from carbon, water, and...
Well, what we're trying to do, great question, because what I think is important sometimes is to shift people's awareness. So why I would say a tree comes from thin air, plants and trees are built from thin air, we're setting people up to be ready to think regeneratively, right? So if you walk into an area that is arid and dry and desertified, if you can grasp that you can build an abundant, flourishing ecosystem out of thin air, that's a perspective change. Does that make sense? Mm-hmm. So while if you just said photosynthesis, that's the process, but the actual substance, like this came from thin air. Like now that it has no water in it anymore, or barely any water in it, this is just straight air, carbon dioxide, that was just taking the carbon from it, connected with hydrogen and oxygen. Like that's what we're dealing with. So to think about that way is helpful for people's perspective to shift, a new view. Does that make sense? Go ahead, Menno.
If I had somebody in the audience asking me, or or challenging this concept, I would say that photosynthesis is the process, but carbon is the actual source.
Carbon. So let's get clear. So when we look at this, there's carbon in the air, right?
Right.
And the plant leaf is utilizing energy from the sun. So we have inside the leaf, there are cells, and what they're doing, chloroplast cells, they are taking the energy from the sun they sip in the carbon. We'll just jump right to it. Stomata, okay? Under the leaf, there are more of these. There are 300 per square millimeter stomata. These are little mouths, shown more directly as little CO2 monster, but they're pulling in CO2. This many per square meter, 300 per square millimeter, sorry. That's a lot, and there's way more underneath the bottom side of the leaf, which we'll explain in a second. But they're pulling it in, and then inside the chloroplast is a little machine, if you will, that's using, like I said, pretend it was plugged into the wall for its energy, okay? You got that? And then it's saying, okay, we're going to take hydrogen and oxygen, combine it with carbon from carbon dioxide, break it apart, put it together, make carbohydrates. That's all happening inside of this machine, okay? So we say, okay, now we're going to unplug it. The cool thing about this machine is it's actually a solar panel, okay? Does that make sense? We don't have to burn coal to make this work. This is a solar panel, so it's actually using the energy to combine to make those sugars, which are energy themselves, combined for us to consume. Does that make sense? So to say the carbon is what's building it is true. The carbon from carbon dioxide is building the structure. It's our CO2 monster. Here we go.
And the O2 comes out of the little monster also.
Yes. Yeah, so when we're talking about oxygen being put back into the atmosphere, the little monsters are putting that out too. Cool?
Yes, so the CO2 is actually getting broken into carbon and oxygen by the sunlight. Is that
Thank you, Elliot. Yes, so that's breaking apart and then recombining. Thank you, Elliot. So breaks apart, recombines to make carbohydrates. Question?
So yes, my question is, I was watching some of the videos from week 3, and part of the talk is, sorry to go ahead a little bit, part of the talk is like things are working together, right? So to try and like grasp this idea that everything's coming out of thin air and that it's only carbon, kind of like the element that we're kind of focusing on, because I think a lot of us, and I speak for myself, that we know that there's a combination of several things happening. It's not this one thing working by itself. It's because of the sonatas opening, it's because the water's there, it's because all these different elements, the sun's coming in, everything's combined, and then it's like a perfect combination for it to do the next step, right? So I guess that's, if I'm hearing people correctly in their questions, is around that, right? Like, where does it come out of? Thin air, and to think that it's only one thing that it's connected to seems too simple.
I love that.
You know what I mean?
You're pushing the holistic thought,
right.
and I love that. But part of the reason that this whole slideshow is existing is based on the current conversation that's out there.
Right.
So we're talking about this in the context that we're in. So depending on who you're talking to, this might not, and that's why it's so awesome that each of us has this independent voice, an independent audience, and a way to communicate this. For who I'm talking to is mostly environmentalists who grasp the current scenario with carbon in our atmosphere. That's my usual audience. I'm trying to give them a new perspective on how to see carbon and to understand the pump that's happening. So, oh my God, a tree was built out of thin air. That's giving me a new perspective on the future, okay? So now we're going to talk about the next thing. Healthy soil is also built from thin air. So we opened up this presentation today with, we didn't really understand how the soil worked, okay? So I'm going to jump to this side of my screen for a second. But normally what you'll see in textbooks of how soil is built is sand, silt, and clay erodes from the mountainside and is here, right? And then things on the top of the surface decompose and turn into leaves fall, animals die. They mix with the sand, silt, and clay to make soil. That's generally what we were taught in middle school and even a lot of high school and some college textbooks. That's how they're talking about how soil is formed. What's the problem with that? The problem with that is a majority of the decomposing stuff that's mixing with sand, silt, and clay does what? Decomposes. What does decomposing mean? It's turning back into CO2, releasing carbon, becoming CO2 again. Okay? We respire CO2 because we're burning the energy, right? So when we grasp that only in about 10, lucky case 20%, usually around 7% of what actually makes our soil is from that decomposition, that's when this is the big news. Healthy soil is built, pardon me, because the plant pumped the sugars down through their roots. This is the big aha moment that we all got, okay? So here it is in a quick second. So we're saying this is the stomata under the leaf. This is a complicated slide I added last class because people were having these questions. We're basically talking about carbon. We have carbon sequestration, carbon going down, right? Through here. The plants are sucking it in. And then this soil, all this is respiring, meaning there's carbon dioxide going up. But what did I explain earlier? Plant leaves have lots of stomata on the bottom of their leaf. This is not a random design. They have a bunch of stomata on the bottom of their leaf because, look at this, all of this respiration happening, carbon dioxide coming up. Look at this small carbon cycle. Check this out. Look at how teeny this carbon cycle is. It goes up, yum yum, CO2 monster eats it, combines it, makes it into liquid sugar, and pumps it, builds the plant with it, and then pumps some of it, usually around 40% average, but sometimes up to 80%, pumping it out of the root. So what do we get? Over time, we get a carbon gain because we're having more pumped in than is going out. More is turning into humus, that stable form of carbon in the soil. It's turning to humus. It's no longer decomposable. It's this magical substance. And that's why we're getting building soil to happen. Versus this situation when we have no plants on the ground. All we're having is carbon soil loss. Does that make sense? So that's when we talk about, when we're saying, oh wow, we're adding carbon to this equation, it's thanks to plants. Grasses are double-sided photosynthesizers, by the way. So they're like the underside of a leaf, but both sides, the whole entire freaking plant. Grasses are just epic. Like nature invented the dopest thing. But they're literally just, the whole thing is most of the time photosynthesizing until the stalk shoots up. Does this make sense? Any questions on this? Yeah.
If I wanted to display that at my tent, because it is very cool.
What I would say is try to find a higher resolution PNG of this file, because when you blow this up, it's actually a low-res file, so you'd have to get a... I'm just saying, these aren't really high-res, so if you go any bigger than this, it won't look really dope. So that's
yeah, no, I just meant, it's like this stuff, like, can I pull these off and turn them into things?
100%. These are all yours. You can mess around with them. You can change, plus soil, adding soil, whatever you want to add.
So you know tilling a cover crop is clearly recommended.
Right, so if we're leaving the soil bare, no cover crop, and then we're tilling it, we're oxidizing, we're allowing more of this to oxidize, meaning we're exposing more of those aggregates to death, and that's CO2. And that's why covering the ground, like everyone who's like being green by like less straws, cool, but being green should be just make shit green, pardon my language, but make everything green, because green is what keeps the carbon going in.
So that's why you want to
The
have...
slide on the...
Huh?
Excuse me.
Go ahead.
The slide on the right, where we see the bare ground, is that supposed to represent typical agriculture, which is not covered by any cover crop or grass, and essentially whatever organic matter is in the soil is releasing carbon dioxide constantly?
Yeah, and thank you, Elliot.
It's also overgrazed land. So it could be anywhere where the soil is bare. It could represent anywhere. It could be after a fire. It could be, anything that makes the soil bare. Typically in agriculture, it's going to be tillage and then not planting anything for a long period of time, letting it lay fallow and bare, or it could be overgrazed land that has desertified.
Or undergrazed land.
Exactly, or undergrazed. Whoever said that, bonus point. So one of the simple ways of taking this is the soil is alive. Why? Because there's a bunch of life in it, right? And what does life need? Food. What's the food? The sugars, right? The sugars that they're pumping out. They're eating these things, or things that ate them, right? What's happening here?
Nobody's eating it.
No food.
There's no food. So what do? They become crazy and they eat themselves out of house and home. They literally eat their house. Literally. Because all the structure of the soil here that's made of carbon aggregates, they start eating it because they have no carbon left that's being pumped in. So that's another way to think about this. You can just present this whole thing as an eating equation. Things need to eat. If you're not having more food go in, they eat what's in the house, including the kitchen sink. Everything goes up. When you eat things, it turns into carbon dioxide. Most people grasp that. Yeah, Meadow.
So that way, I'm pulling it from everything that we read this last week. So when they talked about like why agroforestry doesn't work as well, is it because, so if you have like a big tall bunch of trees and they're not doing that little corner part right there where the monster is eating the carbon and it's going back down again, is it because it's not, because it doesn't have the stomata at the bottom, so close to the ground? Is that part of it?
That's a great extrapolation. So what Meadow just extrapolated was that oftentimes in terms of how quick we can build soil and sequester carbon in a straight forest system, though we have massive trees, we have a lot of space for oxidization or respiration to happen, and not necessarily as quick of a turnaround. But that's why the invention of nature inventing grasses is so epic, because in these regions where it's more dry, we need something that can perform really well and quickly and maintain and protect this soil. Yeah, great observation. Okay, so we call it the big exchange. This is what we're saying is this: when the food analogy comes in, the plant, any plant, say it with me. Any plant is pumping out, represented as the carbon in white, pumping out liquid carbon out of their roots in exchange for minerals and water. Okay, so they're saying we are going to feed you fungi and bacteria and everything that eats fungi and bacteria because you are making available to us minerals and water. Okay? Anybody want to say that out loud? Every plant. So you can serve every plant.
Every plant is pumping carbon out of its roots in exchange for minerals and water.
Awesome. Nailed it. So this is important. This is the big exchange. This is why life on land works. Period. No one can argue with it. This exchange is why there is life on land. We're getting that plants, the photosynthetic super phenomenon, are sharing sugars with the fungi and bacteria and other soil organisms. That's why life on land works. That's why soil was built. That's why we have fresh water. That's why all these things work, okay? Fresh water meaning coming from underground springs and all this sort of stuff. Okay, so here is a photo from David Montgomery. I just emailed him today asking for a higher res version that doesn't have his PowerPoint that I took a picture of from it. But what this is showing us is the tip of a root.
Right.
So tips of roots aren't that small. Just say it so it's in your head. Tips of roots, they are not that small. Why this is important is because we're learning that this exchange happens. It's not just the roots that are doing all the work. So this is the root, and out of the root, plant exudates. So when we talk about plant exudates, what that is imagine sweating sugar out of your arm, okay? And then imagine if you were sweating sugar out of your arm, probably a buttload of bacteria and other things would be like, I'm going to party on Finn's arm. And you probably should take a bath more often. But the point is you'd have a lot of life happening here, right? Because you're feeding them sugar that you're sweating out of your arm, right? Mm-hmm. That's what's happening. This blue hue is the party. These bacteria and fungi represented are way, 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 way bigger than they actually are in real life, right? They're just, we needed to be able to see them. The point is, so this hue here is representing the sugar party that's happening. Bacteria are here. What's going on is it says microbial metabolites enter the roots. Who can explain what that means? And then I'll explain it if you don't get it perfect. Just try it. Why is that happening? Microbial metabolites are entering the roots.
The fungi are making certain nutrients available to the plant, and thus they are able to enter the plant.
Perfect. That's what's going on over here. Let's explain right here. Because this is the bacteria one, but you can just say the same thing with bacteria.
Okay. Bacteria are making available nutrients to the plant.
How are they doing that? Let's give some.
They metabolize things, and then
They become
their byproducts are
plant available
allowed to
things.
be.
Right, so if we have, exactly, so if we have the soil, whatever you want to call it, the sand, silt, clay, whatever is in this matrix outside here, the bacteria's consumption, processes, being eaten, things eating bacteria, bacteria half eating things, what they're making is available nutrients for the plant. We're going to get to this later when we get to human health and soil health. But this is a catchphrase for you to get. Plants don't digest the soil. Plants don't digest the soil. Who digests the soil?
The bacteria.
Microorganisms, bacteria, fungi, and others. Plants aren't actually doing it. Yeah?
I have a question.
Yes.
I thought that the plant could not absorb bacteria or even the minerals that the bacteria had absorbed directly, that they needed bigger creatures like nematodes and protozoa to eat them and shit out whatever.
Great question, Elliot. Thank you for bringing that up. We know, at least I know, there are certain elements that are only available when, as Elliot was mentioning, like a nematode eats certain bacteria. So when we talk about a soil system that's dead, and we understand that there are certain trace elements that are only available if a nematode eats a certain type of bacteria, we're saying we better work on making sure that nematode is eating that certain type of bacteria. Otherwise, we don't get that in the food we eat. So Elliot, from my understanding, it is certain trace elements are only available when certain chains of consumption happen on the microbe level. Does that make sense?
Yeah. I think it's more complicated than what I'm understanding at the moment.
It is more complicated than even what I'm saying. And this is trying to make it in as lay way as we can. But what you're saying is totally correct.
Yeah, I'm just going to add one quick thing on that. So a given bacteria, which you need a microscope to see at 400x, you can barely see it. Inside that bacteria, it's capable of producing thousands of different enzymes. Each enzyme is designed to create one reaction, and it can go in and break loose one chemical element from something and make it available, which may or may not be absorbed through the wall of that bacteria. But literally, enzymes by the thousands are produced by a single bacteria, and we don't even know what all the different enzymes are. So we don't know what all the different bacteria are. We don't know what all the different fungi are. We'll probably never know at that level what's really going on. And you can go even smaller than that. So viruses are smaller than bacteria. All we know is that microbes make all this stuff happen and make elements available to plants.
So in other words, it's way more complicated than we can think.
Exactly. Awesome. I just looked at the time, and we're gonna have to go through here.
The diagram that you're referring to right now?
Yeah.
So the fungal hyphae. So the sugar that's exudated around the root, does that function? So obviously it like gives nutrients to the plant, but does it also function as like a medium for the like microorganisms to like feed the plant? Does it do both?
Well, that is, yeah. What's happening around here is the microbial metabolite, they're soluble and available for the plant. So that's why this relationship is happening and this big party is going on, is there's this exchange, this is representative of that exchange zone, so to speak. Okay, we have to jump to fungi right now. So fungi, you can see, are entering the plant root. That is actually entering. Imagine when you get an IV, right? It plugs into your arm. This is plugging into the tip of the root. Then the fungi, they're called hyphae. The roots of the fungi are called hyphae. They extend out into the soil. This is what that looks like. Oh my goodness. Okay? This is the tip of the root. These are the hyphae. What they're doing is expanding the root capacity of this plant tens of thousands or hundreds of thousands of times. Now just grasp this for a second. Each of these strands is able to quite literally mine rock. They put out enough enzymes to literally burrow holes into rock to get certain things. So when we're talking about this, this is the root tip, and all of these hairs are out there pulling in minerals. This is going to blow your mind, okay? Really quick, actually, let me stop for a second. If you're at a party, you can use your arm, and everyone has hairs, even if don't have as many as other people. Everyone can say, this is the tip of a root. This is how small it is, right? Now, every hair on my arm represents a strand of mycorrhizal fungi. Now let's imagine grossly that my arm hairs are this long, and they're going out into the soil, right? That gives people a connection to like, wow, it's not just the tip of the root. They're using mycorrhizal fungi, and the cool thing, so check out what's happening. The plant is feeding the mycorrhizal fungi sugar so that they can grow. So they're pumping liquid sugar out of this tube. Guess what? The mycorrhizal fungi is collecting water and minerals. And this is what the tube looks like. Mycorrhizal fungi are pumping minerals and water this way back to the plant. And the plant is pumping sugars this way, liquid sugar, and there is no barrier. We don't know how it works. It's a biodirectional flow, and we don't know why they don't mix, and it's just epic. So that's what's going on. We have little traffic going with minerals and water. They're mining it, and check this out. You can't see it in this picture quite, but there are exobladders, meaning like honeycomb structure bladders that these mycorrhizal fungi make that hold water. So anytime in drought, they'd be like, we got a water reserve here. It's like, instead of a bladder like a balloon, like imagine a honeycomb bladder where water is being held there. So they make little bladders. Phenomenal. It's just crazy.
I just love how humans think they're smart.
I know.
You can't see that to the naked eye.
You can't see this to the naked eye. And if you see what looks like very, very fine white stuff, it usually is tons of these things. So you can see it with the naked eye, but you can't see individual strands with the naked eye. So here's a very zoomed in picture. This is without mycorrhizal fungi. This is with. What happens if cobalt or boron or magnesium is right here? Those are essential trace minerals for plants to be fully functional and not be attacked by pests, right? What if it's right here? So that's what we're saying, like those pumps are happening all over the ground. And remember the story I told of one of my priming moments? Do you guys remember this one? When I was helping Cornell with the study, Cornell University, they were studying how oak groves were somehow protecting themselves from airborne diseases. These networks connect plants and connect as far as 10 miles away, which was the study we were doing with Cornell, oak groves, sending messages like the internet, yo, BTW, airborne virus coming your way, get your antidotes ready.
Wow.
So yeah, we think we're smart. Oh my gosh, talk about the internet. As our internet has gone up, we've destroyed their internet, and that's super sad.
Is this another reason for diversity with your crop also because of the length of the roots and everything? And so some are on a shorter level or depth or whatever also?
Yeah, I mean, everything in diversity is for a reason. It's playing a role because we'll get into that more later. We'll get into that more later. So Avatar? Yep. This is the crazy stuff. Avatar, why did this happen in Avatar?
What happens in Avatar?
Because the director, who's the director? James Cameron. Guess who he talked to? Paul Stamets and Suzanne Simard. No, not Leonardo DiCaprio. He didn't know yet. And still doesn't really totally know. Did we watch Suzanne Samard? So he talked with Paul Stamets and Suzanne Samard. That's why this is an avatar.
That's so dope.
Because this is the real deal. So understanding that this is real and we're having to pretend it's real is kind of crazy. So now we're going to talk about the carbon again. So we look at this dank nugget. Some of you know that reference in other terms, but this is awesome because we're talking about aggregates, and next week you'll see them in real life. But look at this. Oh my gosh, this is what I forgot. So this is the big one. Sorry, there's going to be no exercises for today's presentation because we've taken too long. So this is the big phenomenon. What are these hyphae made out of? Their structure. Carbon. This is the big one. So every one of these strands protects itself with a coating because they need to protect themselves from oxygen and other weathering issues. They protect themselves with a coating of this sticky substance called glomalin. That sticky substance let's just give an example. In a prairie ecosystem, imagine a nice biodiverse prairie ecosystem, right, in your head. The carbon and the soil structure that's built there, 60% of it is because these carbon strands, as they age, they fall off the root, and they're sticky substance, right? Imagine these long, tangly, sticky substances. Double-sided tape, right? Mm-hmm. Gum that's in a long strand. What happens when you throw it in? What happens when you throw a piece of gum in a sandbox? Right? What is that called?
Aggregate.
It's aggregating the sand together, right? So that's nature's epic invention, is as this happens, as the plants are growing, as these things are dying off, these sticky, long, noodly things are combining superstructures that can house things and can hold 20 times their weight in water, and these amazing, phenomenal superstructures that are healthy soil aggregates that we just saw. This nugget is because of that. Does that make sense? It's aggregating the soil together in micro aggregates and macro aggregates. These are obviously macro aggregates. So that's phenomenal. And the other cool news, bacteria also produce glues that do even smaller aggregates and help their gluing process. So carbon pumped into the ground up to 80%. Again, what did Don say about numbers? Be really clear with numbers. Certain times of the year, in certain conditions, with certain things like certain tree crops, they're pumping 80% of their sugars, all the carbohydrates they make. Sometimes they're pumping 80% of those sugars into the ground. Usually it's average around 40%. So use 40% just to be safe, because if you go and tell people it's 80%, they're going to argue with you. Does that make sense?
Up to 40% or 20 to 40%.
Yeah, just be safe. But this is, I'm sharing with you because you all need to know how amazing it gets. And what happens if some issue happens above ground? There's all this stored carbon that's available and helpful for plants to maintain their capacity to live. So carbon glued aggregates. Look at how beautiful this is. Nature took, arguably 3 to 4, maybe 5. I don't know how long it took to evolve it, but this is evolution. This is research and development. When this thing can hold 20 times its weight in water, as we'll see next week, hold its stability when you put it in water. This is superstructures. We know more about the movement of all of the celestial bodies, as Leonardo da Vinci said, than we know about this. Still. And you might think I know a lot, but we don't know anything. We don't really know how this is all. We're going to learn so much in the next 5-10 years. Cool? There it is, humus. Just clarity, this is not all necessarily humus, okay? I was just trying to get it represented. So this is what the textbooks didn't teach us, is this pump of carbon. So when you watch the soil story now, it's obviously done really fast in 5 minutes, but this is the big revelation. We were taught stuff's decomposing at the surface of our ground. We weren't taught that carbon's being pumped in and turned into carbon-filled aggregates. And that's why So exudates. So we talk about exudates, glomalin, and more, like making these things. So we go back to that original slide that Don was working with. And our quote from today from Charles Macy, solar energy function. What we're talking about, and you'll see, this is a new slide, so you can copy this one to yours if you want. The green plants are making this work. And this is making the green plants work. And they regenerate over time. And it makes it hold more and be able to hold more and be able to hold more. Nature evolved that way. We learned last week about regenerative being upward curve. If the plants are pumping in sugars, creating aggregates that hold more water, and that means the plants can photosynthesize for longer because there's water stored here and they can access it. That means if they can't photosynthesize without water, yes? Right. So this over here is going to stop photosynthesizing in about a month after rain. This one might last 3 or 4 or 5 months. Again, numbers, don't quote numbers, right? I'm just giving you generalizations. But the point is, if we have healthy soil and we're building healthy soil, our plants are going to photosynthesize for longer. If our plants photosynthesize for longer, we build more healthy soil. Positive regeneration. And we're cooling. And we use less water. So it's a constant, nature invented this. This is epic. This is it. This is the answer to literally every problem. Throw one at me, this will be the answer. I promise you, this is it. Like,
but it's if you plant it with diversity, you know, if you do like a monocrop or a month, like you have to do it with diversity.
Thank you for saying that, but what you just said, you have to do it with diversity. I will bring in one crop of grass from my yard, and we have soil aggregates. We have soil stability. So all these people who took out their lawns in Los Angeles and put decomposed granite, they're not doing anything for when it rains here and helping the ecosystem function more. Yes, is biodiversity 100% helpful? Yes, but as Kevin was talking about, like, how can hemp be bad? Well, I say when hemp's planted in the ground, of course it's good. But it's what happens between the seasons. Are they tilling? Are they using chemicals? How long are they leaving the soil bare before it? Are they doing cover crops? But when a plant is in the ground, if it's green and photosynthesizing, it's pumping how much? 20 to 40% of its sugars into the ground, helping to regenerate. Like they are designed to help the system regenerate. Regenerative means what? Increasing ecosystem carrying capacity over time, regenerating the system to function better, to function at its highest state. Yeah?
So what I heard you say was, if we keep plants planted, if we have roots in the ground, soil can act as an indefinite carbon sink.
Yeah, I mean, we know at this point, or this is a great way to say it. We have had several people in the community of science say, oh yeah, there's probably a topping off point. But then it gets broken all the time. And we're like, well, we don't really know. And we talked about last week, who cares? If we get to the prime condition, which no one in humanity can even trace back to when that was happening in any culture, when we get to the prime function of the ecosystem, fine, sustainable's awesome, whatever, right? But we have no idea how to grasp what that is right now. We don't know. Like, you talk to Alan Williams, who's one of the most prolific guys in this, he says, we have no idea what healthy soil really functions like. We have no idea. Like, that's important to know. Is this a healthy soil system? No, that'd be like going and being like, you know, to that track team you ran against in high school, being like, they just run around the track, be like, these are our track, like this lame track team, be like, that's the best track team. And then you go to the Olympics and you're like, wait, what? What I'm giving an analogy of is some of our research that happens at universities. They do trials with people who don't really grasp this whole thing, and they push this out to the world of like, this is how it works. This is how much we can sequester carbon. It's like lame numbers. And then you have people over here who are experts at this, have been doing it for 30 years. They're like, why is everyone quoting these pitiful numbers? See what I'm saying? We're just not grasping how much potential. So this is what I've concluded as one of the simple ways to do this. So reading this, the big difference between conventional and regenerative agriculture is whether or not you're treating all soil as a living organism that constantly needs to be fed carbon via living plant roots. Does that make sense? So when we see conventional agriculture and people forced into this degenerative feedback loop, we're basically saying, what if all of agriculture started treating this living soil system as a living soil system? It would be different. And we talk about, oh, I never switched this, forget this slide, but the point is I was supposed to move, these are opposite. I moved the graphics because we always go bad to good, but I didn't move these symbols, so please move them if you want. They're correct on your own slideshow, they're just, it's flip-flopped. So this is what we get to. Atmosphere, currently 750 billion tons of carbon. Biosphere, currently 550 billion tons of carbon. Pedosphere, which means soil. Was that in your test today? Yeah. Great. 2,300 billion tons of carbon. More than these combined. Where do we hear about carbon being stored? In our atmosphere and in trees, right? We all have that from our memory. Does anyone talk about carbon in the soil? No. There's still currently way more carbon in the soil. Al Gore just came out with a slide, finally, added to his deck, that building soil carbon is 40 times faster, approximately, than planting trees. Why? Look at this. Look at this. I say guys, so pardon me, I say guys. I'm sorry, I don't mean, some people get offended by that, but this is a mat. Tree here, grass here. There's so much more space. We talked about how great it is to have space in the soil. Yes, that's awesome. Airspace. But how much more space is there up here? When we start to grasp, yeah, planting trees is awesome for carbon sequestration. Building a mat of carbon at arguably sometimes 19 tons of carbon per acre per year at good levels. There's no question.
Just to capsulize
Yeah.
this thing. If you want to have a lawn and you don't use pesticides or artificial fertilizers or too much organic fertilizer, then it's good.
There, not necessarily. So there's so many things. So what is too much water? Or, you know, is your grass long enough? We're going to talk about planned grazing and all the degenerative things, but when your grass isn't long enough, your roots are literally shrinking to feed enough structure, carbon, to the plant so it can continue to photosynthesize. So you rip up a bunch of lawns that have the short grass in LA, their root systems are like this. You can just rip them up like a carpet because they haven't let their photosynthesis, or the leaves photosynthesize and be long enough, so, 6 to 7 inches. They cut them down to 2 inches. The plant's not able to function.
That's why it always looks burnt when you see short grass as opposed to long grass that looks healthy.
Oftentimes, because you're basically, your roots are compensating and they're pumping back the sugars to have it go big, and then we cut it again every week. Jeez Louise. So there's so many ways to make a lawn regenerative, biodiverse mix. There's now grasses that you can purchase that are 6-foot deep root systems. Like, these are things like, duh, that's going to mean it's a more healthy system. It's going to hold more water, retain more water. But you have, imagine a carpet, a really thick shag carpet out in the sun with water in it versus your thin carpet with water in it. Which one's going to be dry faster? These questions.
Can you repeat the number that you stated a minute ago about the capacity for healthy soils to capture soil versus planting trees? Would you say
Great question.
like 40%?
So I'm waiting on Al Gore's slide, but my friend just emailed me because they saw him in Georgia. So let's not quote this yet, please.
Yep.
As soon as I get it, I'll bring it to this class. But he just put up a slide that's basically saying 40 times faster carbon sequestration when we're building soil versus tree planting. Something like that. So we got to get that slide from him, see where his data is coming from, and I'll get that to you as soon as I can. Please don't quote it. But that's basically what we're saying is, if we really grasp how much tonnage of carbon is in a mat of soil versus sporadic trees, it just kind of starts to make sense. Does that?
Yeah, the source of the data, the source of that would be the most helpful thing to have.
Of course. And I'll as soon as I get that from my friend, anybody who wants to say who was at the last talk, his slides do update. So if you're a part of his training, what is it called again?
Citizens
Climate Reality, yeah, Climate Reality Project. So I'm a part of it, but I don't know where my login is for it. So this is a thing that can help you if you are not wanting to memorize all this stuff. You want to lead. I know it's 9 o'clock, but we're almost done. You can use this and just talk about it, being like, hey, so here's me talking about this because I memorized my speech. Here's the plant. And then something else is going to pop up on screen. Here's the carbon dioxide going into the stomata, right? And here's the water going and being absorbed. Then you can talk about your mycorrhizal fungi. They're using their enzymes. The plant's feeding them carbon, and in exchange, they are putting the carbon out, right, into the soil, and then they're pulling in. You know, what I'm saying is you can use this as your presentation. I don't have it memorized right now because it's been a while. But the point is it can take you through, and you can do a quick presentation on your own. Clear? Then there's this version that has it all written down for you. So you just can have people watch it. You can always show people the soil story. When we made this, a lot of people just show the soil story and then they explain with slides in more detail with pauses and questions and that interactive. Because just watching it can sometimes be too much for people to get, but you can highlight things. So use any short media pieces. I encourage you, if you're a first-time presenter, utilize short media. It's usually for people, gives them kind of a soft welcoming into something so they can feel collective as like, oh, we all just watched this. I'm in it together with other people. So definitely useful. If you're not super confident as a presenter yet, use a piece and then highlight what you're most passionate about. Or opposite, switch it around. But definitely it's helpful to use it. All right, let's do questions. And today we missed our exercise, so we're going to do it next week. Very sorry. This was a dense week. Let's do some questions, and then we're wrapped up for today. Thank you so much for listening to this session. Any questions? Great. Anyone online? Go,
I just
Jason.
want to say it was totally great class, really interesting, really a lot of stuff. So thank you very much.
Thanks, Elliot. Jason?
It might be a little bit of a good question or a dumb question, but how do we argue the planting grass thing? Is it because we're planting the wrong grass, because of the watering of it and everything else, or how do we talk about that?
So the easiest way to talk about it is in non-confrontational way. And what I would encourage for that is basically saying, similar to cows aren't the problem. We're going to get into that next week. Cows aren't the problem, it's the way we manage them. Grass isn't the problem, it's the way we manage it. So taking that approach, being like, is grass currently a problem to the person you're talking to? Yes. However, or take this for a second, what if we have higher, cutting grass? What if we have different species of grass that are drought tolerant and have deeper root systems? What if we are having that grass so it's on a landscape where we're harvesting the water that whenever water falls? What if we have more tree canopy that's protecting that grass and somewhat shading that grass so the evaporation rates are lower? There's so many ways that we can practically have grasses because they're the superorganism of the earth, really, if we think about how epic they are for keeping brittle environments functioning. There's nothing else out there. I mean, they were invented to make brittle environments be able to hold mass amounts of life, like the bison or the amount of huge herding animals. Grasses in very brittle environments, utilizing water the best. Just for your own use, pull up the roots of a taproot or pull up the roots of a tree and compare them to pull up a grass. Look who's got winning in the aggregation, in the sponge making. That's where you start to see like grasses aren't the problem. How we're managing them is the problem. Does that make sense?
Yeah. That's what you meant by it when you put in the DG because you think you're doing something good because you're not using as much water, but you're actually killing the soil because nothing can go through that.
So when we get our epic rains, you get 100% runoff and evaporation. Someone who's got 7-inch grass, they've absorbed a ton of water, literally, per acre, 27,000 gallons. If they have zero runoff, if they have an acre plot, they've pulled in 27,000 gallons of water directly in, absorbed, or infiltrating to underground aquifers. And DG, all evaporation or runoff. So just thinking about that, you miss out. It's not necessarily bad. Perfect. Any other questions?
Yeah. It was a good class, a lot of information.
So much information, and it's probably overload. Reminder as we go away, compost is awesome, not because it's just adding to the soil, because it's bringing back the life that helps plants photosynthesize more. It's bringing back the life and the slow-release nutrients that make plants photosynthesize more. So if you just put compost out to make your soil better, it's all just going to oxidize over time. If you have plants in there, it's going to help them photosynthesize more, and it's going to give them the biology that's going to make them share more. That's why it's a regenerative substance, not because you can just put it on and voila, your soil's good.
So what is that time? Because I have a bare ground, I mean, my office is a perfect example of just sand. So I need to put something down and then plant something, but the plants won't grow. So what do I do? Put compost and then leave it there?
Let's say bye to everyone online unless they want to hang out. We're officially, you can leave if you want to, but there's some questions lingering here. Thank you all so much. Let's just wrap and then we'll ask questions.